Great. Thanks everyone for coming. I'm very happy to have Julio here today. He does lots of cool stuff. And this research program in particular is really interesting. So I'll be excited to hear what he tells us about whenever you're ready.
Thanks a lot, Seth, for the invitation. I'm happy to visit virtually, at least, hoping to meet some of you in person in the future. I want to tell you about this program that's been going on for the last couple of years. I've only been involved during the last year or so, to try to see if we particle physicists and people who calculate scattering amplitudes can say something about classical GR and help. All of this comes from originally the great and amazing measurement of gravitational waves at LIGO, and I think many of us ask, can we help? Can we do anything to help this effort, and even as particle theorists? And I think it's important that there are several phases in the Inspiral, the binary Inspiral that is measured by LIGO and other gravitational wave detectors, and there's some phases which are inaccessible to the type of techniques that we use in particle physics, and other things have been developed, like numerical GR or perturbation, black hole perturbation theory, or like the perturbation theory in a curved background. So these are the merger and the ring down phases of the of the binary merger. But there's this Inspiral phase where the two bodies are far away from each other and just rotating around the center of mass, and this is still a perturbative regime. So here there's like, in this two-body system, we can apply perturbative techniques, traditionally the post-Newtonian perturbation theory, to study it. And this is mostly what I'm going to focus about. And the theoretical input in this problem is essential. Like in collider physics, where many times experimentalists, if they can avoid looking at predictions by theorists, and they just look at the backgrounds and kind of try to understand without just everything from the data in gravitational wave physics. This is what the data looks like, and from this mess you have to dig out like the first observation of gravitational wave, and this is done using a template bank of the waveforms of different events. So this is each point in this plot just represents like a waveform for a given mass ratio, and then they basically take an index product weighted by the sensitivity of the detector to extract and see like which signal is closest to the actual measurement. So it's important that we have some theoretical prediction for these waveforms, and the current pipeline looks something like this. So there's some perturbative calculations. This like, for instance, get a two-body Hamiltonian from GR, which is some gauge-dependent quantity, coordinate-dependent quantity, also kind of the multiple moments of the binary, which tell you how the binary radiates. And these are calculated at fixed order in post-Newtonian or post-Minkowskian perturbation theory, which I will explain in detail what it is in a second. And then taking some input from other places like the probe limit and numerical GR, then they build a so-called an effective one-body model, which is what is used to create these templates. So there's an input from many communities, and this is the part that I will be talking about today. But in a sense, we are still like a couple steps removed from the actual templates, but our goal will be to get something like a two-body Hamiltonian. And I think there's many things to learn here.
Julio, what order in the post-Newtonian expansion is the experiment actually set to?
So right now, LIGO, it will be sensitive, I think, up to 6 PN is what is needed. So this is V to the 12th in a velocity expansion. For the early Inspiral phase, the problem is as you approach the merger, then
then you have to somehow match onto numerical relativity or something, right?
Right.
And
so
what
the
is
goal is 6 PN.
What is the state of the art?
I will tell you. Almost all of 6 PN is known. 5 PN was completed allegedly a couple of weeks ago. It was announced this week that the last missing pieces are known now. But So yeah, all of these are like very recent developments. The full term that is complete for a while, it's 4 p.m. I will mention now in a second what is known.
Okay. Sorry for jumping the gun.
No problem. Yeah. Yeah. So I think beyond what is needed for the actual experiment, I think there's many things to learn also, like theoretically, which are interesting. And well, we're gonna have like tests of GR and deviations from the experiment, but that we will understand how to deal with kind of things like finite size effects of compact bodies, so-called love numbers. We'll learn Newton's equation of state. We know a lot about geodesics on a fixed background, but we don't know so much about gravity away from the probe limit. And this regime tests also gravity away from the probe limit. And there's also other formal aspects that one might be interested in. For instance, what is the dynamics for BPS black holes in supergravity? And is there like special theories which have special properties like integrability of the orbit, something like that? So I think there's interesting theoretical questions and also relevant for experiments. So what I'm going to do today is do what I call a theoretical experiment. So ultimately, we are interested in this binary Inspiral, which is a bound system. But of course, we cannot access that using scattering amplitudes. So what we're going to do is an experiment. We're going to calculate the scattering amplitudes, and from them, we're going to try to extract this two-body Hamiltonian and other observables that then we can relate or use for the bound problem, which is the one that is measured at LIGO. And the way we're going to do this is by calculating scattering amplitudes in quantum field theory, which we have now many tools, modern tools to do and to go to very high orders, and then take the classical limit or understand which pieces are relevant in the classical limit and then just capture those. But the goal is to get it like Hamiltonian or a potential. So there's multiple approaches.
I missed something maybe at the beginning. This Hamiltonian, this is a well-defined observable in R, this Hamiltonian, or
yeah. So the question that you can ask is if it's local. It's off shell. It's coordinate dependent. So the Hamiltonian is not an observable. So as I was going to mention now, one of the routes is you start with a scattering amplitude, you extract a potential, which is gauge dependent. And then with this potential in a given coordinate system, you can calculate actual gauge invariant observables, things that you could measure for like the waveform, the scattering angle, the impulse on one particle, the radiated energy, radiated angular momentum. But this goes through some like gauge dependent quantity, which is this two-body Hamiltonian or two-body potential. And this is well defined. It's, at a given order, it stops being local in time because you can have like retardation effects. It's only instantaneous at the first few orders, which is the ones I'll be talking about. But obviously, in the end, because we're doing like relativistic physics, this separation in between like potential radiation, it's gonna break down. But at least at the first few orders, and in particular in LIGO, there's a separation of scales. Like the scale of the orbital motion is very different from the frequency of the gravitational waves which are emitted. So one can this separation of scales works. The Hamiltonian might not be local in time, but that's the only issue that arises. So ultimately, we want to get measurable things, gauge invariant observables, and we are going to start with the scattering amplitude. And there's many routes to this. There's classical routes like the iconal techniques, which you get like a phase shift, and then or a iconal phase, and from that you can get some of these observables. There's this EFT matching that I will describe, where you actually extract a potential or a Hamiltonian from the scattering amplitude. If you're interested in dissipation in QFT, you need to use like real-time dynamics in formalism, and you can measure like the difference between some observable in the in or the out state. So all of these techniques we use, and they complement each other. And I'll be trying to describe some of this today. So the outline of my talk is I'm going to explain what is the QFT setup that we use, which methods we use from amplitudes to calculate these classical amplitudes and these observables, how we understand now better the semiclassical approximation from amplitudes, and how we can use that to make that connection to classical physics more transparent, and then I will flash some of the recent results at like 2 and 3 loops. both in n equals 8 and in GR. So any questions so far? I said many things. I didn't explain anything. Now I will start explaining things. So okay. So post-Newtonian versus post-Minkowskian. So the usual perturbation expansion for this bound system is a post-Newtonian expansion, which is an expansion both in small velocities and in GM over R. So basically, this is the effective social radius over the distance between the particles. So they're far away from each other and they're like moving slowly. And these two scales, they're related because it's a bound system, so it's virialized. So they all have the same order. And so the first term I guess this was not post-Minkowskian still, but post-Newtonian still. So the first term in this expansion is just the Newton potential, which is known for a few centuries now. And then the correction, so there's like the V squared correction, which goes the same as like G squared over R. This was computed by Einstein and friends a long time ago. And there's been slow but steady progress in going up this like vertical direction, which kind of relates different orders in velocity and G Newton. And the latest results are like 5PN is being computed by two groups, except for two coefficients. And apparently the second group, Bini, Damore, and Gralico, have found these like last few terms missing in the 5PN Hamiltonian. So the state of the art now is like partial computations at 6 post-Newtonian order, also like one piece at 7PN. What is post-Minkowskian perturbation theory? It's an expansion only in GM over R. So it's still long distance, it's still classical. There's a small parameter, but the velocities can be relativistic. And this is natural for a scattering process where you can have the body scattering again at long distances, but moving as fast as you want. And this is kind of a more modern approach where we calculate one order in G Newton at a time, but all orders in velocity. So this captures a whole series of PN terms to all orders in PN, but a fixed order in G. So it's kind of trying to get the same information, but organized in a different way. And like 1PM, I think there's an older calculations, but the one that it's presented in kind of a modern form was like 2008, and the 2PM it's only known since 2016. 3PM was a couple years ago, and then this year we presented like most of the 4PM result. There's some missing part that has to do with this time non-locality. But basically, the most important part of the 4PM Hamiltonian. So this is the G to the fourth, which is like equivalent to 3 loops and scattering amplitudes. And what we compute is some coefficients of some potential that has an expansion in GM over R. So if you go to GM over R to the fourth, then the goal is to extract these coefficients, and we will do it with scattering amplitudes, and then other people apply it to the Inspiral problem, which is relevant for me. Okay, so that's the basic setup. What we want to compute. So what is a classical limit in our context? So there's 3 length scales involved in this problem. One is the Compton wavelength of the particles. And this essentially goes like h bar over m. There's the effective social radius of the particles, which is like the gravitational length scale. And then there's the separation between the two bodies, and which essentially goes like h bar over the momentum transfer in some scattering process. It's just like the Fourier transform essentially. So we see that there's 2 small parameters, which is the ratio of each one of this with this. From now on, I will just set h bar equal to 1. So 1 is q over m. So this is an expansion in the separation, like over the Compton wavelength, and that encodes like the quantum versus classical expansion. So corrections in q over m are more quantum. And then gm times q encodes these pm corrections, because the Fourier transform of this will give like the 1 over r type potentials that we want. Notice that this is not ordinary perturbation theory in gravity. Ordinary perturbation theory in gravity, which is a non-relativizable theory, it's perturbation theory in G times the energy squared, or G times the m squared, basically energy over m Planck, which has to be very small. And so in fact, it's kind of the opposite regime, because here we have Gm is much greater than 1 over m. So in a sense, it's not, well, not in a sense, it's not perturbation theory in the ordinary sense, in quantum field theory that we would do for like scattering amplitudes in gravity. And that means that we will be collecting terms to all orders in perturbation theory. So like, classical terms actually are a whole series of things. Like the traditional example is all the ladder diagrams resum into something like an Ekman phase, which expresses like the Newton potential or like the leading order exchange of classical gravitons. Okay, so we will be digging these corrections from inside the scattering amplitude. And what we do is we essentially integrate out all of the internal structure of compact bodies, like whatever we have, black holes, neutron stars, we just write them some like minimally coupled scalar, which will create like some like point particle excitations, which effectively encode the dynamics of these guys. If you are actually interested in their finite size effects, in the fact that we have black holes versus neutron stars, you can add higher dimension operators to this effective action, and these encode like the tidal deformabilities or like gravitational polarizability, this kind of effects, and this can be included systematically. If we have also done that in some papers and other people. Similarly, if you want to include spin, you can make this massive high spin field and just calculate scattering amplitudes of particles with spin. So in terms of the amplitudes, as I said, classical doesn't mean tree level because we are digging out these like GM times Q corrections to higher orders in G. So we will be calculating loop amplitudes. If you're confused why loops can contain classical corrections, the easiest way to say it is that the h-bar scaling in a massive theory is not trivial. Masses also have factors of h-bar, not only the couplings. So as I said, there's this small parameter GM over R. And from the point of view of the amplitudes, what we have is this like Q over M is small, or equivalently, this is kind of a large angular momentum expansion long distances. And in practice, how do we do this? We focus on certain momentum regions. So there's the matter lines that will have like a hard momenta, and then there's like graviton lines which will have soft momenta, which are suppressed by these inverse powers of angular momentum. So J is just Q over M basically, or M over Q. So what you should remember is that the nonlinear and G corrections, they're encoded in loops with these soft gravitons, with these classical gravitons. Okay, so we will calculate the scattering amplitude, but then we will restrict the momenta to be small. So we will expand the integrands so that they're small. And then the contributions that we are missing, actually, they're contributions which are analytic in the momentum transfer. There's like polynomials in Q squared. And these are essentially contact interactions in position space. So these are like short distance interactions, which we can actually not predict with an effective action because we don't understand quantum gravity. So we don't know what those are, but those don't affect these long distance physics that we're interested in. So by expanding the loops in this region, we focus on the physics that we want. And also, if we want to focus on the conservative dynamics, because we want the Hamiltonian in a potential, then in addition, we will have some velocity scaling. So the idea is that you want to turn something which is like a graviton which is exchanged into some instantaneous potential. And that means that this graviton, well, first of all, if you want to integrate it out, it has to be off shell. And that's enforced by saying that its energy component is much smaller than its spatial component, like for its momentum. Okay, so this will give some instantaneous potential. So if I expand the graviton propagator, which is 1 over L squared, where the energy component is small, then it will give something which is essentially purely spatial, so it's instantaneous in time. And there's also radiation graviton. So if you're interested in radiation effects, then you also have to include these other velocity regions. So again, we will expand the loops in this particular way, and we'll calculate these loop integrals. And so the conservative dynamics is encoded in loops with these potential gravitons. So we call the ones that have this scaling potential gravitons.
So Julio, can you just clarify which particles are allowed to run in loops, both gravitons and matter fields, or just gravitons?
Everything is allowed to be inside of the loop. There won't be, for instance, self-graviton loops. It's easy to see that if you have a self-energy loop of a graviton, then that integral, when you expand in these regions that I'm saying, is just scaleless. So so that integral cannot give a correction of the kind that we are interested in. But we will have loops. I will show you some diagrams in a second. But there will be loops where gravitons are exchanged between matter legs, and the loop is kind of two graviton to matter, like a box diagram.
I see. And these loops, maybe you can just clarify for me. These loops are not polluted by higher order corrections to GR, or are they?
By higher order, meaning like
well,
R
it's
cubed,
not.
or
You mentioned several times that general relativity is not a renormalizable theory. So so certain loops have divergences which can only be cured by adding higher corrections in the metric interactions themselves. And
right.
Are you sensing that or not?
So if you have a UV divergence, it will be local. So it cannot give a contribution to these long distance effects, non-analytic in Q, which will yield a potential. What you could ask is if this vertex correction can introduce a correction to the potential. And the answer is yes. If I add an R cubed interaction in GR, there will be a diagram which has that R cubed, but if you power count, like if you just do naive dimension analysis and you ask how small is that contribution, you can compute it. It's computable. We will have an undetermined Wilson coefficient, which we don't know, or maybe in string theory we know it, but it's just very small. So this can be computed systematically, and in fact, there's a few papers by the group at Queen Mary where they have explored like what are the R cubed corrections to the like potential in GR.
And they're smaller than the 6th post-Newtonian?
Yes.
I see.
Yes. Yeah.
Okay, I don't have a good feeling for when they would start to what order would they start to compete? If you say they had an order 1 coefficient?
Let's see. I haven't thought about that, but the problem is that if you don't have a corrections in G that also come with a 1 over R, with a corresponding 1 over R, then it's very small, because basically what you have is, with an M and an R, so you can have corrections which go like GM over R, which are the ones that we'll be able to see, which are kind of classical. And then you can have corrections that go like G times R squared. So this is L Planck over R squared. And typically the corrections that these higher derivative deformations of GR give you, they're of that kind. They're like L Planck over R. So they're very small, because there are no corresponding factors of mass that can come with them. So that's where the suppression comes from.
By looking at operators that are mixed with the metric and the matter fields that you were just talking about.
Yeah, so you can get, but they will be suppressed. So there will be maybe a few factors of GM over R, and then multiplied by like G over R squared. So in the end, it will be like as long as there is one factor, which is G over R squared, without any factors of mass, then it's completely suppressed because it's L Planck over R. So they're extremely small. We can discuss more at the end. I can give an example of how the power counting works. But all of this is computable. Like if you just put an undetermined Wilson coefficient, we can add it and compute. Okay, so how do we actually extract the potential?
Sorry, can I go back 1 second? Just to the matter model, the scalar field that you put in. Let's just see. So just the mass term, nothing else. For the scalar. So is this just the simplest model, or in some sense derived from GR itself? Say?
So you can try to do a matching calculation of like a black hole in GR to this model. You can try to extract these Wilson coefficients here, which encode like the finite size of the black hole. Turns out that at least in the static case, the leading coefficients are 0 for a black hole. They won't be 0 for a neutron star, but it's an effective theory. So it describes the most general thing. The only question that you need to ask is at which order do each one of these operators enter, and which order do they contribute? So for instance, the leading operator affects enters for the first time at 5pn order. So the first deformation, which is called the love number, which is like an R squared correction without derivatives on R, that enters at very high orders already. So the dynamics up to that order will be independent of these operators, and that means they don't distinguish between black holes, neutron stars, whatever you have.
Very good, thank you.
Yeah. Can I ask a question
Yeah.
here too? So in the case of black hole or neutron stars, at some order you would have a dissipative effect due to the horizon or dissipation inside the neutron star. Which order is that? That probably will be.
I don't know from the top of my head, but I can direct you to the papers that that study these effects. So there's a series of recent papers by Walter Goldberger and Ira Rothstein. They do this slightly differently. They work with a Borderline theory instead of with quantum fields, like with scalars, like I do. But they study these dissipative effects from some like degrees of freedom at the scale of the horizon. So we haven't attempted to write or we haven't thought about how to do that in this QFT setup. But if it can be done in the Borderline, there should be a way to do it in our setup too.
Thank you.
Okay. So just very quickly, how do we extract the potential? I told you that these corrections that we're interested in, they're encoded in these loops of potential gravitons, which are soft. So they're suppressed both in velocity and in V, sorry, and in Q. And so what we do is we write an effective theory, which is just like the two particles interacting through a potential. So there's no radiation, no gravitons radiated to infinity because all the gravitons that we integrate are off shell. There's no particle production because these are like classical particles. So all the interactions are just some potential, which we know local because we're integrated out at least part of a massless particle. So you can calculate a scattering amplitude in this theory. It looks very simple. It's just a sum over bubbles where you insert its vertex here. And then you do the computation in the full theory, which is more complicated. And then you require that they're equal. And from that, you can read off this potential, which is essentially a Wilson coefficient. And there's this, as I mentioned, there's these other approaches which are based on word lines, which go way back to like Fion Wheeler and like in a modern, from a modern perspective to the work of Goldberger and Rothstein. Okay, so we want to do this matching calculation. We can also deal with dissipative effects using this in formalism, where we measure some operator in the out state versus, compared to the in state. And then because it's a scattering process, the relation between the in and the out state is the S matrix. So we can write all of these kind of observables in terms of like matrix elements of the S matrix and cuts with some measurement function. So for instance, this is the impulse of one particle, like how the momentum of one particle changes on the scattering event. And if you work it out, which they did in this paper, you find that it's some Fourier transform of a kernel. And this is very similar to a cross-section in a collider in the sense that there's a virtual piece and there's a real piece, like a real emission piece. There's infrared divergences in both that cancel. And then there's some like phase-space integral with some weighted numerator that one has to do. And similarly for like the radiated momentum in Bremsstrahlung, it's very similar. It's something like the phase-space integral over the amplitude with graviton emissions, where you are weighting it by the energy of the gravitons. Here we were weighting it by the energy of one of the matter lines. Okay, so this is all very schematic, but for the people who work on classical GR, this is very similar to the usual form for the radiated energy in terms of the waveform. So the waveform is basically this like emission amplitude, and then you're doing an integral over the phase space, tangential phase space with weighted by the energy. And so basically, you see that the goal is to calculate this classical amplitude, and then we can extract any quantity that we want from them, either like an observable directly or this Hamiltonian or this potential that we can use for something else. So the goal is to calculate this amplitude. So now I want to tell you about that. It's always useful to work on toy models first, and we have a very good toy model, which is n equals 8 supergravity. So we know a lot about this theory. We know like for instance, the integrands for 4-point scattering amplitudes all the way up to 5 loops. And by doing a dimensional reduction, we can actually get scattering amplitudes for BPS black holes in this theory. So if I split like, so these integrands are, they're for maximal supergravity in general, so they're valid in 10 dimensions. And if I split the 10-dimensional momentum into 4D and a 6D part, this essentially, when you look at the SUSY algebra, they give you some central charges for these black holes. So this dimensional reduction only gives you the simplest case where the BPS charges are just like, they just have one relative angle misalignment, which I picture like this, where these essentially are the extra dimensional momenta. Okay, so using KK reduction, for a given massless diagram, we can get like a bunch of massive diagrams in lower dimensions, so we can extract the massive amplitude. And the theory is very simple, so I can show you in one slide the 1 and 2 loop amplitudes, at least as a sum over scalar integrals. So the 1 loop integrand for the massless theory was known a long time ago. It was directly computed in the massive theory also recently by Simon Cron-Howat and his students are. And it's very simple. So these are just scalar box and cross box integral. The sigma is essentially a rapidity type variable. And this is the BPS angle that I mentioned. So this is what it looks like. So there's no, for the numerator, similarly at 2 loops, the massless integrand was known from the 90s. And then by dimensional reduction, we can get the massive integrand for the scattering of 2 BPS black holes in an equal-Z supergravity. So these BPS black holes are essentially KK gravitons from the state. So 3-loop integrands are also known from the double copy, and we can just keep going. So we have data up to 5 loops, so at least the integrand part is solved. And then we just need to understand how to compute integrals.
What is the loop order you need to go to reach your goal in the post-Newtonian expansion?
So if you want NPN, you always need to go to n plus 1 PM. So that would mean 7 loops. Sorry, 8 loops in scattering amplitudes. So it's pretty high.
And
yeah.
state of the art is 5?
The state of the art is in PN is 5, but what happens is that they only have certain, so we would calculate the whole loop at once, whereas they only focus, say, for instance, on the static piece and then the B squared piece. So each order in PN at a given order just needs one more velocity correction. So it's orthogonal and it will get harder.
Is the double copy formula known to hold to that order?
So we have representations up to, like, the representation we have at 5 loops is not, we didn't construct it using the double copy. We constructed it just using unitarity cuts, which I'll explain now. But up to 4 loops, we have a double copy formula. At higher loops, we don't. But we can still use a double copy. So let me explain that. So how do we compute these amplitudes? So the 3 amplitudes, the double copy has been proven through all multiplicities. So for those of you who haven't heard about this, so if you have some amplitude, which is very complicated, so this is some diagram in the amplitude, and then there's a piece of the diagram that looks like this, like a 4-point amplitude. Then there's like an S channel, a T channel, and a U channel version of that, where the rest of the diagram is the same. It's only this sub part of the graph that changes. And the colors of these diagrams in Yang-Mills theory, they will be related by some Jacobi identity, which I write here as like CS plus CT plus CU equals 0. If one can arrange the numerator, the kinematic numerators that depend on polarizations, momenta, et cetera, to satisfy this identity, that in general is hard. It's proven that you can do it to any order at 3 level. There's no closed form formula, but it's proven that you can always do it. Then if you take the Yang-Mills amplitude, which is a sum over color factors, numerators, and propagators, and just replace the color factors by numerators, you get the gravity amplitude for free. Technically, it's gravity plus dilaton plus B field, but we know how to get rid of the states that we don't want. And this also works for classical solutions. So you can look at papers by these people where they also have kind of what is the double copy? What is the thing that double copies to a Schwarzschild black hole? So there's we don't know the precise connection to the amplitude story, but there's the motivation to use these double copy and amplitudes methods to classical GR comes from these works by these people that double copy classical solutions. How do we get the loops? So the trees are basically free if you know how to compute Yang-Mills trees. we use the unitarity method. So what is the basic idea? Just very quickly, the loop integrand of a scattering amplitude is just a rational function of loop and external momenta, maybe of polarization. And then if it's a rational function, it's fixed by its residues. And from physics, we know that the residues are factorization diagrams, which because of unitarity, so they look something like this. So it's a product of three amplitudes. These blobs are trees. All the visible legs are on shell. And then we have to sum over like the states, basically the polarizations. And this tells us what is the residue when we put these propagators, when we set them to 0 for this rational function, which is a loop integrand. So what we do is we write an ansatz for all the diagrams, which are is dictated by locality. And then we require that the numerators agree with all of these residues, and that fixes the loop integrand. And when we do this sum over states, if we have things that we don't want, like a dilaton or a B-field, we can always project it out by inserting some physical state projector that tells us that we just pick out like the transverse traceless part. Sorry, the symmetric traceless part of whatever state is crossing the cut. So for instance, at 3 loops, we just needed these 8 unitarity cuts. That these products of trees encoded all of the information for the classical physics, for the conservative classical physics. Because there's one extra rule that one needs to see that, which if I have time I'll explain, which is that for this to correspond to a conservative process, one needs at least one matter propagator in each loop. So you cannot have like a self-graviton loop. And these 8 unitarity cuts is everything that was needed. If you want dissipation, you need also more like self-energy type things on one or the other, like this. But you can see that the most complicated object in here is basically this 5 graviton amplitude in Yang-Mills, because we can, sorry, 5 gluon amplitude in Yang-Mills, which we can double copy to GR. So that the most complicated input for this calculation was a 5 gluon amplitude. And the integrals, we use modern machinery from QCD. So there's so the details here don't matter so much, but basically there's some spatial choice of variables where we parameterize the external momenta like this, in terms of some like hard part and some like soft deviation, such that when we expand in this subregion, so what does the subregion expansion do? I told you that P are much harder than L, so all pieces that go like L squared are small, so I can just throw them away or just expand. And what happens is that matter propagators get linearized. They look something like this, where this is the 4 velocity, so all the mass dependence factors out. And because of this choice of variables, the only dimensional full quantity that these integrals depend on is the momentum transfer, and that is fixed by dimensional analysis. So you just have a 1-scale integral left to do. So this is true to all orders in perturbation theory. So the integrals that we need to do are just a function of the velocity of the process, or of the sigma variable that I wrote. Y is just it's just the version of sigma that takes into account that we are kind of using this slightly different parameterization. And the modern tools we have from QCD are things like differential equations, where we reduce the whole set of integrals to a basis of integrals, which are called master integrals, using integration by parts identities. And then these satisfy differential equations that look like this, where epsilon is the dimensional regularization epsilon. And at 3 loops, we also have some elliptic integrals, but we can still write differential equations. They just don't look as simple as this. So instead of actually doing integrals,
what does it mean to say it's a velocity differential equation?
So the only variable is this sigma, which this sigma essentially is like a rapidity, or also you can think of it as like 1/√1 minus v squared. So this is essentially the relativistic factor, the relative gamma factor, Lorentz factor between the 2 particles. So the only variable that all of these integrals depend on is the sigma, which is the velocity, the relative velocity of the 2 bodies. So what these differential equations do is, if you give me a boundary condition, which is the first order in the velocity expansion, then the differential equation resums the whole velocity series. So essentially, if you give me like Pn data,
is there an a priori physical? Is there an a priori physical meaning of velocity equation itself, the equation itself?
So there is a sense in which the differential equation restores Lorentz invariance or like boost invariance, but it doesn't look like the differential operator that we are applying is just a derivative with respect to this variable sigma. So it doesn't look like a boost generator. We are not saying like the boost generator must annihilate the amplitude, but maybe there is a way of rewriting it like that. I haven't tried, but naively is something that just resums the velocity series in such a way that you get something which is Lorentz invariant. Okay, so maybe I don't have that much time, so I'll just flash this. So the boundary conditions are essentially trivial to obtain because you, as I said, you just have to expand in the low velocity limit. So the matter propagators that look like this, they're homogeneous. The graviton propagators, the energy component I told you in this potential region. So remember I said that L went like V1 in the potential region. So the energy component is much smaller. And if you expand, they become like purely spatial and instantaneous in time. These are essentially delta functions in T or derivatives of delta functions if you Fourier transform. So everything you have is an integral where the only energy dependence or like non-trivial energy dependence is in this denominator, so you can calculate it by residues. So everything is very simple once you have this differential equation, and there's a similar prescription for these other regions like radiation that we have developed. Okay, and the last thing I want to tell you is that bear with me. This was the technical part of the talk. Is how we get these phase space integrals. So we also have ways of encoding these, of calculating these phase space integrals in a very simple way. And the basic idea comes from some older papers in QCD, which is called reversion unitarity, which is basically it's a simple observation that if you have a delta function, an on-shell phase space delta function, you can always write it as a difference of propagators with different I epsilon prescription. So whatever technique you were using, differential equations, integration by part, everything still works in the same way for these on-shell phase space integrals. Everything exactly applies. The differential equations that we get there, they're essentially the same differential equations, and we can use the same techniques. In addition, since we can calculate the virtual integrals using these differential equations, sometimes we don't even need to compute new things because we can use things like the cutting rules to extract like phase space integrals from the imaginary part of certain virtual integrals. But worst case scenario, we have differential equations that look like this. So this like, sorry, this should be a y, not an x. But y is essentially sigma. This is a velocity, like this is a Lorentz factor. So they look like this. So some derivative of the integral that I want, it's related to another integral. So we can solve these kind of differential equations. Okay. So this is kind of a different story that I want to tell you now, but it was very useful to do these calculations, which was think, okay, we are computing things in scattering amplitudes, but the scattering amplitudes are quantum objects. So how do we make the connection to classical physics more manifest? And in particular, this is actually a technical necessity, because what happens is that if you have an amplitude, say at order g squared, there's going to be contributions that you want to extract, like this potential, which is actually order g squared. But there's also going to be contributions that come from like multiple insertions of the lower order potential that you need to subtract. Okay, and these ones actually scale worse than classical, in the sense that if this leading order term is 1 over h bar, as usually we have for some classical quantity, all of these ones are going to have 1 over h bar to some higher power. So intuitively, this comes from the fact that the amplitude is basically e over h bar. I will be talking more about that. So it just comes from expanding this to higher orders. So this has an expansion in g Newton, but then the expansion overlaps. Different orders in g Newton overlap from the point of view of the amplitude. Okay, so is there a better way to compute these things that avoids having to compute all of these iterations and subtracting them? And can we organize perturbation theory in some nice way so that we can avoid computing these things? And the basic idea is that scattering amplitudes in this conservative sector, they're purely elastic, because as I told you, they only contain, these matter lines only exchange off-shell gravitons. Nothing is going off to infinity. There is no particle production. So usually unitarity of the S matrix, we write as an equation like this, which tells us that the imaginary part is a sum over all cuts that include like 2-particle state, 3-particle state. In general, it's a very complicated set of nonlinear relations. But for the elastic amplitude, we only have a 4-particle amplitude. So I don't have any emission or particle production. So it's more convenient to write the amplitude and as an actual phase, which is obviously the simplest way to solve this equation manifestly. And then the question is, what is this phase? And what this phase is, as an operator, is the logarithm of the usual scattering amplitude. Okay, so I can expand this logarithm formally as a product of things. So these are operators, and that means that whenever I have amplitude square, I need to insert a complete set of states, which in this case are just 2-particle states. So if I want to calculate directly the exponent, which is the thing that will have a nice 1/h-bar expansion, that at worst has a single 1/h-bar, then I just need to compute the amplitude and then subtract like a bunch of iterated 2-particle cuts of the same amplitude. And this thing, if I actually calculate the expectation value, it's a familiar object. So for instance, if I choose a state with fixed energy and angular momentum, this is the usual scattering phase shift. And in fact, if you do a partial wave expansion, what happens is that this 2-particle cut is diagonalized. So it just becomes a product in the same way that the Fourier transform turns a convolution into a product. And the partial wave expansion turns this 2-particle cut into a product, and one can solve, I mean, you just find that this delta is a number, which is the phase shift. What is that number? So we are familiar with the usual semiclassical approximation, right? For some object in quantum mechanics, that if we have some state with initial like coordinates and time, then we know that to leading order in h-bar, this transition amplitude is given by e to the I over e to the I times the on-shell action over h-bar. Okay, but importantly, this only works with appropriate boundary conditions, right? So even the classical variational problem is only well defined with fixed coordinates at the beginning and at the end of the path. That's okay. So these terms are just the equation of motion, but the boundary term only vanishes if we have delta q equals 0. So an amplitude is more like a transition element with fixed energies and momenta. Okay, so the object that we have here is not the usual action, but there's this other object that differs by some boundary counter term. So this boundary counter term, the p dot q, what it does is it cancels this variation of q at the endpoints of the path, and instead you have delta p, which is fixed. So this is fine. And similarly, because we are at fixed energy, the time of the 2 endpoints of the path is not fixed because we're fixing the energy. So this term cancels the variation of the time at the endpoints of the path. Okay, so it's this object that relates to the scattering amplitude. So what is it? So the old object, like the usual semiclassical action, if you choose nice variables like angular momentum, energy, if you choose like a subset of like angle action variables, it looks something like this. So these ones are like conserved quantities. So it just looks like angular coordinate times angular momentum, energy, the time of the process, and then there's this thing which is called the radial action. So the radial action it looks like this. So it's the integral of the radial component of the momentum along the trajectory. So this classical action is basically this radial action, which is a purely classical quantity. And this is what we get when we compute the phase shift. So you might be familiar with the usual iconal approach, where you also find some sort of exponentiation. This is similar, except that because we take seriously that we are expanding in spherical waves rather than plane waves, then there's some angular corrections that are under control, which are important at high orders. And this object has can be connected directly to classical gauge invariant observables. For instance, by taking derivatives with respect to angular momentum, we get the scattering angle of the process. If we take derivatives with the energy, we get the time delay. There's something called a Detweiler redshift, which you can get by taking derivatives with respect to the mass by keeping other things fixed. So these are the usual like thermodynamic type relations that one gets from this object. Even better, oh, sorry, before I get to that, I told you that the objective of this was some technical difficulty, and in fact, this exponential structure, it tells us how to organize the amplitude. So we can organize it in some way that looks like this, where we have a finite part, and then we have a part which is an integral, like that encodes these sort of corrections that I was drawing before, like this, that I don't want to compute because I already know. So this exponentiation structure makes manifest the terms that will cancel automatically, and it lets us read directly from the finite part of the amplitude this radial action, which is connected directly to classical physics. So this I already commented, that it's slightly different from the usual iconal story, if any of you are familiar with that. Okay, so even better, this quantity can be directly analytically continued to the bound case. So so in this paper by Kalin and Porter, which is very nice, they explained that the integrand of the radial action for the unbound like dynamics and the bound dynamics, the integrand is the same. The only thing that changes is the endpoints of the path, which are the orbital elements. And it turns out that that these are related by analytic continuation. So the minimal radius of approach in the scattering problem by analytically continuing in the energy, and also by flipping the sign of angular momentum, gives you the endpoints of the path of the classical one. So there's a formula that looks like this, where you take the difference between like plus j and minus j, analytically continue to negative energies, and you directly get this object for the bound case, which is the one that we're interested in for LIGO. So in fact, that gives you formulas for the periastronaut bands, for instance, in terms of the scattering angle, or for the orbital period of the bound system in terms of the time delay. So we can directly relate the observables in the bound and bound problem. So the proof of this is purely classical. This is done using classical mechanics. We don't have a kind of quantum mechanical proof, but I think it would be very interesting to understand how this works in mechanics. Okay, so I just have 5 minutes, so let me flash some results. So this is, for instance, the radiated momentum in the scattering of two black holes. So both in GR and n equals 8 supergravity, it takes the same form, where these h's are some rational functions of sigma, which was this velocity variable. This is the impact parameter. These are the four velocities. So it's actually not that complicated. It's a two-loop calculation. We need these two unitarity cuts. We calculate things as I explained. And in fact, we match the post-Newtonian expansion that some people had computed. So there goes all the way back to Kovacs and Thorne, which calculated like the first correction to this. And over the years, people have computed more and more. In fact, Amor told us that he has computed privately up to 9 p.m. and he agrees with our result. And also Veneziano, Di Vecchia, and friends, they've reproduced our calculation only a couple weeks ago. And there's we're working out other observables, things like differential observables, like the differential power spectrum, or angular distributions. So these are very similar to collider observables, like PT or rapidity distributions, or event shapes in colliders, things that people are interested in lately. I think it would be very interesting to study things like the energy, the angular distribution of the energy and the celestial sphere, but also like the memory, like things that people who also like to think about kind of BMS and what's going on at sky are interested in. So also the impulse on a particle.
So is that just for the charged black hole case in analytical way, or
no? The structure is the same in both theories. I'm not showing you what these rational functions are, but the structure is the same. For the charged black hole, it's just that these functions depend on the angle, on the BPS angle. But they're very simple functions. They're like sigma to some power over square root of sigma minus 1 to some power. In GR, they're more complicated. But yeah, I'm just, these functions are messy, so I'm not showing them to you. I'm just showing the structure. Okay. So similarly, for the impulse on a particle, using this in formalism, we can find very nice formulas. For instance, the full impulse at order g squared. This is the Fourier transform of the impulse, but basically the transverse part is directly the real part of the one-loop amplitude. The longitudinal part is directly the imaginary part of the one loop amplitude. And there are similar formulas at higher loops, which show very nicely the connection between the amplitude and these other quantities. So for instance, here I'm showing you the n equals 8 result when I set the angle to pi halves. So here I just chose one of the angles, otherwise there will be some angle, some BPS angle dependence also there. So okay, it's just some complicated function of velocity, but it is what it is. So this is the result of two loops. Okay, so the last thing I want to show you is the actual amplitude that tells us the potential. So this is what the amplitude in n equals 8 looks like. So sorry, I'm flashing all of these complicated formulas at you, but the structure is very simple to understand. There's a finite part, there's a 1 over epsilon, which has to do with this breakdown of the splitting between like conservative and radiation. So this is understood. If you're interested, you can ask me more about that. But interestingly, this part here is directly related to the function that I showed you in the previous slide. So it's known that this also gives the energy loss or the radiated momentum in the scattering at the previous order. So this calculation is completely different, but we find the same result. And then there's some finite part, which is some complicated function. And in particular, in this case, there's no test particle contribution, which now you'll see there is one in GR, because the BPS black hole metric is actually perturbative in G. So there's only the probe result, it's only kind of or linear in G. Okay, so there was this conjecture if the orbits of black holes in n equals 8 were integrable. So if there was no precession to all orders put forward in this paper, and what we find is that at 3 loops, up to 3 loops, it works, but at 3 loops, there's actually precession. So this indicates that probably the n equals 8 is not integrable, like the orbits in n equals 8, they're not integrable. GR is more complicated. The structure is the same. The only difference is now there's a probe part. So there's a piece here which is not suppressed by powers of the mass. So this is the variable that you take to 0 to go to the probe limit. So this you can calculate using the Schwarzschild metric. And okay, we agree with that in this probe limit. And the rest is more complicated. Now there's also some like elliptic function showing up of the first and second time. And of course, we can check this against like the potential that we get from this amplitude. We can check with all the available data up to 6pn, and we agree. And as I said, this coefficient is related to the other calculation that I flashed, and it's also a non-trivial check. Okay, sorry about all the complicated formulas, but you can get an idea of the complexity of these objects, because at the end of the day, even though they're classical and they're just corrections to Newton's potential, they're still a 3-loop calculation in a nonlinear theory. So they're pretty complicated. There's something interesting, which is that at G cubed, if you calculate the scattering angle in n equals 8, sorry, there's a typo here, and in Einstein gravity, it's actually universal at high energies. As a leading order, this is well known. There's a famous paper by Tuft where he shows that essentially 3-level dominates the high energy limit of the graviton amplitude for any theory. It's the same. What we found is that it actually, both in the conservative case, it works. If you restrict to conservative, there's a log divergence. If you include radiation, this log divergence goes away, and it actually it's actually still universal. And it matches all results by Veneziano, Amati, Ciafaloni, where they calculate this for massless scattering. So as expected, energy scattering of massive particles just becomes massless scattering, and it's universal. So we've computed these things, at least in the massless case, we've computed them for all supergravities with n greater than or equal to 4, as well as from first principles in GR, and we find that the angle is the same at high energies for all of these theories. So this is unexplained so far. We don't understand why. And the last thing you might ask if you're interested in experiment is this useful or not? So the G cubes of potential from a couple years ago, it showed a good trend. So it was not as good as what was being used for LIGO. So you can look at this paper if you're interested. But now the group by Bonanno and friends, they have to produce this nice plot for us. So let me explain what it is. So this is the binding energy, which is the gauge invariant observable that they use to test how how good your Hamiltonian is. This is how many cycles before merger you are in the binary Inspiral. And this dashed line here is the numerical GR result, which is the truth. Okay, so you can see here the first few PM orders, they're all pretty close to each other, so they don't do super well. But actually, the models that they get using our 4 PM Hamiltonian, they're valid essentially up to 2 orbits before merger. So you can see that when you get to 2 orbits before merger, you're like at a 0.4% error. And this is already the accuracy of the Hamiltonians that they're using nowadays in LIGO. Even though, I mean, this essentially it contains the whole like 4 PN information that is being used at LIGO. It's unclear how the high orders. Go ahead.
Can I ask a question? This is maybe slightly flippant, but numerical relativity can simulate the whole cycle, the whole period before the merger. Advantage of having the analytic formula for the Hamiltonian.
Right. Yeah, they can simulate everything, and that's why we have this curve going, like we know what it is up to the merger, and we know what the truth is.
So what is the advantage of the analytic formula?
Oh, okay, the advantage is that you cannot run one numerical GR simulation for every point in your parameter space to create all of these templates. So there's like hundreds of thousands of templates, and if you wanted to know exactly what the dynamics is for each one of them,
computational cost to produce the black curve is very high.
Yes. So these models are also tuned by looking at comparing to numerical GR. But also, I mean, the disadvantage is that if you want to have an understanding of which different effects are coming in, and for instance, if I ask you, okay, are you sensitive to this deviation from GR that you were asking about? If the Wilson coefficient, if the scale that you think made them very small is not the scale that actually appears, that question in numerical GR, it's hard to see at which order you would be sensitive or where you could search for this. But by having an analytic handle, you can try to understand these questions. But anyway, the message from this plot is that it seems to work. It seems to do as well as the things that they're using right now. In fact, for a certain part, until you get late enough, it does even better than the current models. And a complete comparison requires basically computing some missing part, which will cancel this 1/epsilon that showed up in the result. So this is what we're working on now. So as I said, if you're interested in what that effect is, you can ask me later. Okay, so sorry, I run a little bit over time, so I'll stop here. So hopefully I convince you that there's these modern tools which are very efficient to compute scattering amplitudes, and when we put this together with ideas from effective field theory, we get some scalable way to compute classical potentials and observables in classical GR. In fact, we've reached the state of the art in the computation of some of these quantities, not of the potential in the sense that there's like high orders in PN, but for instance, this radiated momentum, we provided the first like Posning-Kaskin calculation. And importantly, the methods are not close to being exhausted. So it's clear that maybe not me, but it's clear that someone can go to high orders. So along the way, we've improved our understanding of this semi-classical limit of the amplitudes, improving on the usual iconal techniques, which I didn't talk about, but basically at leading order, it doesn't matter, everything looks the same iconal, this semi-classical exponentiation that I talked about, but at high orders is important to understand what really is going on. And there's a key challenge that remains, which is how to translate some of these observables that we compute with radiation from the scattering to the bound problem. So this radiated energy, we could translate directly also. I didn't show you that, but we also get the radiated energy in the binary Inspiral. But it was unclear if this can be done for other observables. Turns out that this morning, there's a workshop going on right now at the GGI in Florence, and there was a talk by Rafael Porto where he explained that it also works. So these analytic continuation techniques from scattering to Inspiral, they also work for a more general class of observables. So this should give us more power to use scattering amplitudes to learn about the things that people care about for LIGO. So I think I'll stop there. Thanks.
Great. Thank you so much, Julio. Let me clap for everyone. That was very cool. Lots of very cool things there. So we've had lots of questions. Any other quick questions before we maybe take a coffee bathroom break and then chat more? Okay, well, maybe we've exhausted things for now, but we'll take the break to think of more questions to ask. Great, let me stop the recording.